Welcome. Today we are diving into one of the most mind-bending concepts in statistics, Berkson's paradox, where data filtering creates fake correlations. Ever noticed how some people say, if someone's really attractive, they are usually not that nice? Or in college admissions, the brilliant ones often have poor test scores. Or maybe in dating, the more charming they are, the less sincere they seem. These observations might feel true, but they are not always. In fact, what you are witnessing might be a statistical illusion. Welcome to Berkson's paradox, a weird, mind-bending glitch in your brain's data processor. Let's bring this to dating. This diagram explains it beautifully. You generally date someone for either their looks or for their personality. So here, these are the two categories, an attractive person and unattractive person, a kind person and a mean person. And who would you choose to date? There are three subclasses: attractive and nice people, attractive and mean people, unattractive but kind or nice people. But what don't you date? Unattractive people who are also mean. These people or this group is filtered out. So in the people you do date, the attractive ones are split here. The attractive ones are split across kind or nice people and mean people. But the mean people you date, that is this, they are all attractive because the unattractive ones were never even considered. This creates the illusion that attractive people are more likely to be mean, when in truth, looks and personality were never related to begin with. This is Berkson's paradox in action. The illusion arises not from the people, but from how we filtered the data. This paradox occurs when two completely independent traits appear negatively correlated, just because we are looking at a biased slice of data. This happens when we filter people based on some combined criteria, like only considering those who are good at either acting or singing. So in this slide, we have generated 10,000 people who are rated or who are scored on acting and singing independently. The scores are from 0 to 100, and both these scores are centered around 80. And both these scales, acting and singing, are not correlated to begin with. So this is the original data set. Now here's where Berkson's paradox sneaks in. We apply a filter. We keep only those whose combined acting and singing scores exceed 160. Sounds fair, right? We want only the elite performers. Now look what happens when we apply this filter. That is, acting plus singing should be more than 160. Suddenly a negative correlation appears, which means a good actor is a poor singer and a good singer is a poor actor. This is Berkson's paradox in action. Selection bias has created a relationship that is not real. Now let's try a different filter. Let's keep only those people who are good at both acting and singing, and not just good, but closely matched in both the skills. The result is a positive correlation. This filter reveals a trend where people who sing well also act well. But again, it's not a property of the full population. It's a result of how we filtered the data. So now we will do a Python demo of the same problem where we'll simulate 10,000 people. We'll assign them independent scores from 0 to 100. These scores will be having a mean of 80, and then we will investigate the Berkson's paradox. Welcome. Let's continue to explore one of the most surprising ideas in statistics, that is Berkson's paradox. It's when two completely unrelated things like acting and singing start looking like they are negatively correlated, but only because of how we filtered the data. So let's begin by importing standard Python libraries: NumPy for numerical operations and random number generation, pandas for manipulating the data, matplotlib and seaborn for plotting, and I have imported a function called Pearson R, which is used for calculating the correlation coefficient. So first, we are going to generate simulate 10,000 people, and we are going to assign them random scores on acting and singing. So let's see. Let's define a variable acting, and I'm going to generate normal distribution having mean at say 80, a standard deviation of let's say 2, and we have to generate 10,000 people. So this is how I'm going to generate the acting. So remember, this has come from a very independent Gaussian distribution. I'm going to do exactly the same thing for singing. And so these are two different talents, and they're coming from two different distributions, as you can see. And now I'm going to combine both these scores in form of a table. So let me call that table as data, and I'm going to generate a data frame. And how I'm going to do it, I will define the first column as acting, and I'm going to pass all the acting scores there. And then I'm going to define another column called singing, and I'm going to pass on all the singing scores there. So hopefully this should work. Let's have a look at our data. I'm just going to have a sneak peek of first 5 values. So let me run this code. Okay, so this is how our data looks. So these are number of people going up to 10,000. I'm just seeing the first 5, and they have been given acting and singing scores randomly. So since these scores are random, they should not have any correlation. So now let's calculate the correlation between the acting and singing. So let me call it correlation data, and I'm going to use Pearson's function for this. And what this function is asking for is the x variable and y variable, and then it will calculate the correlation between x and y. So in our case, x is our acting data and acting score, and y is singing score. So it should give me two outputs. One is the correlation coefficient between x and y, and the second is p-value, and I'll just explain what p-value is all about. So let me just first print this. For that, I'm going to correlation coefficient, which is my correlated data, and I'm going to extract the first answer, which is correlation coefficient, and then I'm going to print p-value. Correlation data, and then I'm going to this value, p-value. Let's see whether this is functioning or not. Yes, it is. So the correlation coefficient is 0, which reconfirms that there is no relationship between acting and singing, and that's quite evident because these two variables are independent and they have been drawn from two different Gaussian distributions. So they obviously are not related to each other, and hence the correlation is almost 0. And this p-value is low, which shows that it has a lot of confidence in this correlation. So p-value signifies how much confidence you have in the result. The lower, the better. So this is good, and now what we can do is we can also visualize what's happening here. So for that, let's plot a figure. Let's say figure size is 5 by 5, and I'm going to do a scatter plot. And what this function looks like is like this. We have to pass data and x and y, and then the scatter plot between x and y will be plotted by this function. So my data here is data, and my x is acting score, and my y is singing. And I'm going to, let's see if everything is all right here. Yes, so clearly we have acting on axis and singing on y, and nothing is correlated, so it's all a random mess. There's no pattern which is emerging. Let's just create some more visuals. So I'll just create a horizontal line on the plot showing the mean of the y data, and it will have a color black, and I want a line style which looks like dashed. So let me just run this, and yeah, you can see there's a dashed black line which is at the mean of singing scores. And I will also plot the vertical line, and this time instead of horizontal it will be vertical, and instead of x it will be instead of y it will be x, and rest everything remains the same. So you can see here now this is the mean of acting and this is the mean of singing, and these black dashed lines are tracking that. And let me also give it a title: scatter plot of original data. Okay, so here we are, scatter plot of original data, and no pattern emerges from this data, and hence the correlation coefficient is 0, which was expected. Now let's apply a filter, and what I mean by a filter is that I want to have all the elite people in the in my data set to remain. For example, they should have very high score on singing and acting. So basically what I'm trying to do is apply a Berkson style filter and see its impact. So how it's going to happen is like this. I'll call this data filtered 1, and I'll take original data and I'm going to do this: acting plus singing. These scores for everybody will be added, and this should be greater than 160. That means both above average. I'm looking for elite talent, and this is how I'm going to filter out my data, original data, and I'll then see the impact of this filtering. So again, I'm going to view my data. So let's say data filtered, and I'm going to see the first 5 rows. I'm able to see the scores here. So combined score will always be more than 160. That's what this table is showing. So now I'll compute the correlation coefficient for this data. I'll call it filtered correlation coefficient filtered 1, and I will use, again, I'll simply copy this and apply it here. So now my data is data filtered 1, and similarly here. Basically, I'm now using filtered data to see the correlation, and I also will copy this print statement to save time, and I'm going to see correlated filtered 1, and again correlated filtered 1 data. Let me just run this code, and now something really surprising happens. My correlation between acting and singing has become negative, and my p-value is very low. That means there's a great amount of confidence that a negative relationship happens between acting and singing. That's really strange. So what can I do? I'll plot the data and see what's happening there. So I'm just going to copy this entire code from here, and let's see what happened. So instead of data, it'll be data filtered 1. I'm passing on the filtered 1 data and acting and singing scores, and scatter plot of filtered 1 data. And let's give it a color, a different color. Let me plot it in orange. So there you are. After filtering, I'm getting this negative relationship. This is really strange. I just wanted all the good talent to remain, and that's the reason why I defined a score of 160. Anybody crossing that score, I will keep it in my data set. But when I do that, a very strange thing happens. The data seems to suggest that good actors, like this one, are bad singers. And if I look at good singers, like this one, very high in score, singing score, but he's a very bad actor. This relationship is a pseudo relationship. It didn't exist in the original data, and it has happened because I applied a Berkson kind of paradox to this data. Very interesting. So let's pause here and connect this to the real world. Imagine a dating app where you swipe right on someone if they are either attractive or kind. Now your matches include charming people and beautiful people, but you never see the folks who are unattractive and mean. Eventually, you might start thinking attractive people are usually jerks, even though in reality, looks and personalities were never related. So let's try a different filter this time, and let's keep only those who score above 80 in both acting and singing, and their scores must be very, very close to each other. That means acting score and singing score should be almost equal. So I'm again selecting elite people from this data set, and let's see what happens this time. So apply a new data filtered 2. I'm going to take my original data set, and I'm going to filter out in the following manner. People whose acting score is more than 80, and their singing score should also be greater than 80, and their acting and singing scores should be close to each other. That means this should be less than 1. So basically, again, I'm catering to very, very elite talent. And I'm going to again calculate correlations. So I'll just copy this data, this code, and modify it. Now this time I'll call it correlation filtered 2. And I'm going to pass on the new data. Okay. And I'm just going to copy this print statement again. And change the data. Okay, so let's see. Oh, so now something really interesting happens. The relationship flips, and now it's showing positive relationship between acting and singing, which means if I have picked up a person and he has a very high score in acting, he's bound to also have very high score in singing. And the fact is that in the original data set, this relationship did not exist. And again, you can see the p-value is very low, which means we have great amount of confidence in this. So why not plot it and have a look what's happening there. Let me just copy this code and paste it here. And let me just change my data to data 2. And remaining things are okay. And this will become filtered data 2. So let me plot this, and also let me just say plt dot show. All right, so strange things are happening once you apply filters. As you can see here, I have now a positive relationship. Let me just plot it in a different color. Instead of orange, let me just plot it in green color. Here we are. A good actor is also a good singer. And surprisingly, all these relationship or pseudo relationships have started appearing because of the paradox, because of the filters that I applied on the data. And this is exactly why people get baffled, and we have to guard against these kind of pseudo relationships. Berkson's paradox is a great reminder that data filtering changes the story. Correlation is not always the truth. Sometimes it's an illusion. Always ask what got excluded. Thanks for joining this tutorial. If you found this interesting, hit like and subscribe. Next time we will explore another paradox that fools even seasoned analysts.